Hey, Mr. Dent here. How's it going? We're still in Chapter 2, Section 2. We're going to be talking about velocity and displacement with uniform acceleration, and then we will add on to that with final velocity after any displacement. All of these are going to be involving uniform acceleration. Okay, so as before in the previous section or on the previous screencast, we're still going to be applying kinematic equations to calculate distance, time, or velocity under conditions of constant acceleration. In this section, you will be using what I like to call a menu of equations. And so the key to using these is just you need to determine what you're given in the problem, and then you need to pick the equation that works with those variables. Now, this is a nice handy table to have because it organizes them by on the left side you have if we have an initial velocity. So if the object is already moving and we want to find something out about it. And then on the right side would be the same equation except it's eliminated velocity initial. So this would be in the case of when the object is starting from rest. So if you look at those, you can clearly see that the right side is just missing the VI. So VI was here, and it was being, we had a sum of, or we had the quantity 1/2 times, or 1/2 times the quantity VI plus VF. Well, if VI is 0, we don't need to include that, so you can just use this shortened version of the equations, and all of these do that. And so, like I said before, the key to this is seeing what you have, what the problem gives you, and then you need to pick the equation that uses those things. Okay, so let's just go ahead and get started with some problems. So here we have a plane starting at rest at one end of a runway. It undergoes a uniform acceleration of 4.8 meters per second squared, and it does this for 15 seconds before it takes off. And then we want to know what is the speed at takeoff. So basically what it's asking is what is going to be the speed at the end of that 15 seconds. And then we need to find how long the runway needs to be in order for this to take place. So this is a two-part problem. One thing you know, and I said this before, we always want to find the givens, and so and I'll just kind of give us some more repetitions that how you need to think about this. So if it's starting at rest, that's definitely that telling us that we have a VI of 0, which I already have shown here. And then it says it goes under uniform acceleration of 4.8 meters per second. So that is going to be our acceleration. So I'm just going to draw an arrow. I'll just go like this, kind of go the same way. So the acceleration is 4.8 meters per second squared, and then and it says it goes for 15 seconds. So there's our time. So I'll go down. And I know a lot of you are going to be reluctant to do this, make your little listing of everything, but I think it's pretty helpful. It helps us, especially in these kinds where we have multiple formulas that we can use, and it helps us make that decision a lot easier. So anyway, let's move on. So we have our givens identified. So we have a VI of 0 meters per second, and we have an acceleration of 4.8 meters per second squared. And then we have a time of 15 seconds. And we want to know how fast it's going to be going at takeoff. So in other words, what is the velocity final? So as I look through these, I want to look for, hopefully I can pick one that has, that it's finding exactly what I need. And so here I have velocity final. However, this is for when I have an initial velocity. And so I didn't have one, so I can jump over to the other column, and it has that formula that I need. So it's finding VF and I have an acceleration, I have a time. This fits what I need to do. So I will just plug numbers in where they go, and it's pretty straightforward. And so so we're finding velocity final, and we have an acceleration of 4.8. Let me make my dot a little darker, meters per second squared. And then that's going to be multiplied by the time of 15 seconds. And we should get a velocity of 72 meters per second. And so that's the first part of the problem. And then so the next part is, how long must the runway be for the plane be able to take off? So we will look for an equation that has us finding displacement, because the how long must the runway be is a distance or a displacement. And so we can look through our menu of equations. So here we have one with displacement. However, since we're given a velocity, we want to find one that also has velocity. And sometimes that's not always possible. So you may be able to use this one. And actually, I think you could use this one because you have the final velocity and everything. But just just to do an exercise in choosing equations, I'm going to pick the one that closely matches everything that I have. So I have, I'm finding displacement, I have an acceleration, I have a time, so I'm going to use this one. So change in x equals 1/2 the acceleration times the change in time, and that quantity is squared. So we just plug in numbers. 1/2 times 4.8 meters per second squared, and then we have 15 seconds. That is going to be squared, and when you do your math, you should get 540 meters. Okay, so we're going to do another one of these problems. So in this one we have a person pushing a stroller. They start from rest, and they're going to be uniformly accelerating at a rate of 0.500 meters per second squared. And we want to know what is the velocity of the stroller after it has traveled 4.75. So since we start in rest, VI is 0, and we're trying to find VF, so that's what we're needing. And it gave us an acceleration of 0.500 meters per second squared. Time we don't have, and we're not going to be using that in this one. We'll see here in a second. And then we're given a displacement of 4.75 meters per second. 4.75 meters, I should say. So step 2 in this is going to be picking the formula that we want to use. So we want to pick one that matches what we have and what we're trying to find. So we want one, hopefully, that has velocity final. And so this one does, but it has an acceleration, which we have, but it has time, which we don't have, so we can't use this one. This one has, so this has velocity final, and it has acceleration, and it has displacement. So this is a perfect match for what we want to do. So we can just plug and chug here. Let's see if I have another slide. No, I do not. Okay, so we're going to be plugging and chugging here. So we're still using this one. So VF final squared equals 2 times acceleration times the change in displacement. So 2 times the acceleration, which is 0.5 meters per second squared, times our displacement. which is 4.75 meters, and that's going to come out to still 4.75 is the quantity. However, our units are going to be, because we're multiplying meters per second times meters, we're going to get meters squared over seconds squared. And we still have VF squared over here. So we need VF by itself. We're going to have to take the square root of both sides. And we get that. We now have VF without a square. And we should get 2.18 meters per second. Okay, that's that. Okay, so let's do this one last problem. So in this one's going to be a little bit different because we do have a velocity initial involved. So we have an elevator. It's moving upward at 1 meters per second. So that's going to be our VI, our velocity initial. And experiencing an acceleration of 0.31 meters per second squared. So 0.31 meters per second squared. And then it goes a distance of 0.75. And then what will its final velocity be? So that's what we're finding here. For some reason I'm having trouble making question marks. Okay, so we have our givens identified. Now we need to figure out which one of these formulas to use. So we want to have, hopefully we can find something that has VF. We're finding VF. So here's, and we do have a velocity initial, so we have to do something from this column. So here we have VF equals a VI plus acceleration times the time. Well, we don't have time, so we can't use that. And so let's skip down here. Here we have a VF squared equals VI squared plus 2A and the change in displacement. That matches everything that we need, so we're going to go with that. So I'll just start right here. So VF squared equals VI squared plus 2 times acceleration times the change in x. So we can plug in our numbers. So we have a VI of 1.20 meters per second, and this is going to be squared, and then that's going to be added to 2 times our acceleration. Now, one thing that I forgot to do here, so in the problem it has this is moving upward, so this needs to be positive, and the reason we generally want to have upward being positive, that matches with the x and y coordinate system. So on the y-axis going up is moving in the positive direction. So this will be positive. So I'll put a positive here, and I should have done that when I was doing my givens. And then our acceleration is downward, so it will be negative. And that will be important because the elevator is moving up, the acceleration is going down, so that's slowing the elevator down. So we should get a smaller final velocity than our initial velocity. So 2 times our negative 0.31 meters per second squared times 0.75 meters. And so we should get, with, I'll kind of do this one incrementally. So we have 1.44 here, and that's going to be meters squared, second squared, And then we have, when we multiply all this out, we should get a negative 0.465. And that's also in meters squared, seconds squared. And that works out, that kind of lets you know that you're doing things right, because you really can't add things that aren't the same with different units. You shouldn't be able to do that. And so this is going to turn into 1.44 minus 0.465, and you should get 0.975. And remember, we're still in meters squared, seconds squared. Now all this time VF squared is on the other side of our equal sign, so I'm going to carry that down. So VF squared is over here, so we need to get rid of that squared. Take the square root on both sides, and so velocity final is going to be equal to, and this is a rounded answer to 2 significant figures, meters per second. And that's what we're looking for. We're looking for a meters per second, and when you take the square root, it removes those squared, so that also is another sign that we're doing things right. Okay, so our final velocity is going to be 0.99 meters per second, and that makes sense because, and that's something that should always occur, your answer should make sense. So that's a good way to kind of look at it and say, hey, does this fit the description of the situation? So since the acceleration is downward, so it'd be like putting on the brakes possibly, or gravity itself. I know the rate of gravity isn't 0.31 meters per second squared, so whoever made this problem up is something that I'm not familiar with. So so that makes sense, though. The acceleration is going against the velocity, so we should get a smaller velocity. And it was a very short distance, so it wasn't much of a change in our velocity. Okay, so the assignment for this video, the worksheets that go with this video are going to be worksheets 2D and 2E. And then you will be ready for the Chapter 2, Section 2 quiz 2C through 2E. This concludes this screencast. I hope you enjoyed watching this screencast as much as I enjoyed making it. I'll see you in class.